Hello, everyone, and welcome to the next lecture in our course Reasoning LLMs from Scratch. We are currently in the reinforcement learning phase of our course, and we have covered a lot of concepts in reinforcement learning in the last several lectures. The last three lectures have focused on the trio of methods used in reinforcement learning to solve for value functions and to find the optimal policy for a reinforcement learning agent. This trio of methods includes firstly dynamic programming, second Monte Carlo methods, and third temporal difference methods. In all of these methods, we looked at a way of measuring the value function for a given state. In the dynamic programming methods, the value function was estimated using a set of equations called as Bellman equation. So we had the exact solution for the value function of all the states. The drawback of dynamic programming is that we need an entire model of the environment. We need to know exactly what is the probability that the agent moves from one state S to the next state S dash. And in most of the real life cases, this information is not readily available to us. That is why we need to change our algorithm in such a way that the model learns from experience. The model learns from interacting with the environment. The agent gets better and better as the agent interacts with the environment. And Monte Carlo methods and temporal difference methods fall in this category. These methods do not require an explicit model of the environment. Suppose I am an agent and I am navigating through an environment and I go from the start state to the end of the episode. In Monte Carlo method, what happens is that if I start from a state and I go to the next state, I go to the state after that, and I complete my episode, I update the value function of my state only after I complete the entire episode. This is one of the drawbacks of the Monte Carlo methods because if I want to update immediately as I interact with the environment, it doesn't happen. You need to wait till the entire episode is completed. We saw a very interesting example in the last lecture where we discussed about temporal difference methods. We looked at if you're going from your office to home and there are seven junctions in the middle and you want to approximate the time taken from each junction to your home, which is the value of that junction. Now, if you are stuck at a junction every single day and there is a huge amount of traffic, let's say on one day you go outside your office, you move, and you're stuck at junction number 3. Now, Monte Carlo method says that don't update the value of junction 3 until you complete the entire episode and reach your home and cover all the seven junctions, which is not very efficient, right? I would ideally like to change the value of junction 3 immediately. In particular, I would like to increase the value of junction 3 to indicate that I have faced a traffic here today, which means that the time taken from this junction to my home is going to be higher than my earlier estimate. But Monte Carlo method does not allow you to update instantaneously. This problem is solved in the third method in the trio of methods, which is the temporal difference methods. In the temporal difference methods, we don't calculate the entire reward in the entire trajectory. All we do is that we calculate the subsequent reward, and the value of the next state is used to approximate the overall reward or the entire return of the trajectory. So this allows us to not wait till the end of the episode, but use an approximate estimate for the return. This approximate estimate is a combination of immediate reward and the value of the next state. So that is the difference between temporal difference and Monte Carlo methods. These try-off methods are what constitute as classical reinforcement learning. And in all of these methods, you might have realized that what we are doing is we have a state and we have a value function of a state. All our methods, all our discussion has always focused on calculating the values of each states. Remember, the first example we saw was a recycling robot where the states were high and low, and then we were calculating the value of each of these states. Similarly, in the last examples with the junctions, we have seven states which represent the seven junctions, 1, 2, dot, 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 7, and then we calculate the values of all of these states. These are what are known as tabular methods. Essentially, you are representing a number, you are calculating the values of all the states, and you are listing that down in a table. That is why these class of methods are called as tabular methods. Now, tabular methods are good, they are efficient, they allow us to calculate the value function of all the states in the prediction problem, and in the control problem, they allow us to even calculate the optimal policies. The major drawback of tabular methods is that in practical cases, the number of states are enormous. Consider the game of chess as an example. So, chess is a game which has a lot of different combinations. There are pieces, and every piece can move in a specific way. So, it turns out that there are 10 raised to 46 states in the game of chess. Now, if I want to train a reinforcement learning agent to learn from experiencing the game of chess, then there are 10 raised to 46 states over here. So if I use tabular method, then I have to enumerate the states 10 raised to 46 times, and I have to calculate the value of each of these states. Now this is an incredibly hard task which takes a huge amount of memory and also time to do these kind of computations. That is why tabular methods, although uh, they are easy to understand, they are easy to discuss in academic settings, they are good as a precursor to modern reinforcement learning, they are not very practical. They cannot be used for practical use cases. And that is why today we are going to understand how can we learn from our previous encounters with the states and generalize to other states which we have not yet visited. For example, if there are 50 states which my agent will possibly encounter in the future, I will visit only 25 states, let's say, and then I will generalize to 50 states. So, this is what we are going to look at in today's lecture. We are going to understand how can we use our knowledge from a limited subset of state space and generalize to provide a good approximation over a larger subset. Now, this is a problem which is definitely something we need to solve if you want to tackle these modern problems with a huge number of state spaces, like the game of chess we saw. What is the first thing which comes to your mind when you hear about this word generalization? When some information is given and you're trying to generalize to data which is not available to you, the first thing which comes to mind is this is familiar. This sounds a bit like regression, doesn't it? Let's say you are given marks of a student, and you are asked and the x-axis are the number of hours which the student has studied. Now the data which you have is, let's say, for 2 hours, 4 hours, and 8 hours, and you get marks of 20% 40% and 60%. Now, if someone asks me, Rajat, can you tell me what will be my marks if I studied for 5 hours, which lies somewhere over here? So now, what I will do is I will simply approximate a function which passes through all these points, and then I will use that function to find what is the value if I study for 5 years. It's approximately maybe 50, 45%. This is called as regression, and it's an extremely common technique used in traditional machine learning. So this is the main appeal of machine learning. You are given a limited data set and you are using that data set to extrapolate to inputs which you have not yet encountered. And you see these examples everywhere. You also see these examples in classification type of problems. Let's say I am given a lot of images of brain tumor, and my tumor is divided into two classes, benign and malignant. Now I train my model on all of these images, and then finally I get a new MRI scan from a patient, which looks very different from all these images I've encountered before. But the idea is that in the training process, the model learns a lot of features from the images, and it is able to understand the data which is not seen, and it's able to make a prediction. So these are common techniques which we use in machine learning. So when you encounter this question, the first thing that might pop into your head is, well, this sounds very familiar. This is function approximation in simple terms, and function approximation is something which people have been doing since a lot of years. Here I have provided another example where you see pink dots which represent the data that is available to us, and then there is a blue dotted curve which approximates this data, and then basically you throw away these pink dots later and you just use this blue curve and you say that this is my model, this is what my model has learned, and given any input I'm able to predict what is the output for that input, even if it doesn't belong to the data which was given to me. So this is the traditional way in which function approximation is being solved. Now a natural question to ask this is can we use this method for approximating the values of states, because the problem seems to be similar, right? We Let's say my agent encounters 25 states and I know the values of all these states. All I have to do is fit a function, and then I need to calculate the value of the remaining 50 or remaining 25 states which my agent has not yet encountered. Well, it's not that easy and not as similar to machine learning problems as we will see in a while, which is what makes reinforcement learning problems slightly challenging compared to traditional machine learning. The main difference is, if you're trying to do something like this, if you're trying to predict the value function from let's say blue is the data given to you. So I know the values of five states: state number one, state number two, state number three, state number four, state number five, and state number six. And someone asks me, Rajat, what is the value of this state? So I'll just simply calculate it from this curve which I have used to approximate this data. Now, the main difference between reinforcement learning and supervised learning methods is that in reinforcement learning, the target function is not known beforehand. For example, remember here when we looked at the hours studied by the student and the marks they got, this is the target function, and we know this target function for a certain number of points, right? We know the value, it's 20% for 2 hours, it's 40% for 4 hours, and it's 60% for 8 hours. Even here we know the target function, it's either benign or malignant. The problem in reinforcement learning problems is that you do not know the value functions of the states before you solve the problem. You only know the value function of the states when the agent has interacted with the environment so many number of times. So before you start to solve the problem, you are not given a table that saying this is the input, this is the output, solve the problem. The output is not known to us, so it's impossible to construct the table before the agent interacts with the environment. Remember, the definition of the value function is the addition of all the rewards which my agent gets in the future. So if I am calculating the value function of state at time t, then a value function is simply given by this. Now these are the rewards, and gamma is the discount factor. But unless I interact with the environment, how do I estimate these rewards? And this is also a stochastic problem, which means that every time you interact or be in this state, you might get different rewards. So you have to calculate an average of all the rewards, cumulative rewards you get in the future. So the target is delayed. The target variable is not known beforehand, which is a problem in reinforcement learning. And that's why, even though the task we are faced is that of function approximation, we do not know the output variable at all unless we interact with the environment. And the second problem is that the target can change with time. For example, if I'm driving, if a self-driving car is moving on a road, uh, in some cases the traffic might be completely clear, whereas in some cases the car might encounter heavy traffic. In which case, uh, whatever the car sees is changing in every episode. So the firstly, the target variable is not known beforehand, and secondly, the target continues to change over time if the environmental conditions continue to change. Because of these two methods, or because of these two issues, it is not as simplistic to apply the methods used in typical function approximation use cases to reinforcement learning. But this is exactly what the purpose of today's lecture is. We are going to slowly make a shift in our mind from tabular methods to function approximation methods. And we are going to get very comfortable with these function approximation methods eventually. So we will learn how to solve the above problems. It's interesting how problems arise and then researchers learn how to take care of the problems. And this again illustrates the value of doing research and the cumulative efforts of how research adds up through series of efforts. And then what we are seeing right now is the result of all these problems which are encountered by scientists and they have solved them. So so now let us understand this in detail. We call this section as value function approximation, and that is the problem that we are trying to solve. So before we learn how to solve these two issues which I mentioned previously, let us try to familiarize ourselves with the notation. We will get comfortable with the notation that is used for the problem, and we will define a structure to solve this problem. Again, the mathematics here is not very complex, and it's easy for even beginners to understand. So firstly, we write down this value function as v hat of s comma w. Remember that previously we used to write the value function as v of s. Now we have made two changes here. Firstly, we use a hat to represent that it's an approximate value. And secondly, we use a letter here called w. This is called as weights. And this is a vector, which means that it doesn't have a single value, but it can have multiple values like 1, 2, 3, etc. So now the value function is dependent not only on our states, but it's also dependent on these weights. which is also called as feature weights. I will explain why it's called as feature weights in a while. So usually this function is used to approximate the value function. People who are familiar with neural networks can make an analogy here by thinking of these weights as similar to being the weights that we have in neural networks, but we'll come to that later in a while. Now, the reason we have these weights is because we express the value function in terms of the states and the weights. So by adjusting the value of the weights, you can control uh, the value function estimates. And that is the whole objective of the value function approximation, is to find out the value of the weights such that the value function, the approximate value function, closely matches the true value function. So these weights you can think of as sort of a controllable parameter using which a wide range of functions can be approximated. Now let's take an example to build our intuition here. Let's say this is the true value function, which is denoted by v of s, and this is the predicted value function, which is denoted by v hat of s comma w, where w is a vector of weights. Now in reality we are never going to get a perfect match between the approximated value function and the true value function, and there are going to be these errors. So you can see this is an error. At every point the approximate value function is not matching our true value function. It only matches at this point, but at other points you see there is an error. Now the objective of the weights is to tune the weights such that we minimize this error as much as possible. And to minimize the error we use a notation which is or we use a metric which is the mean square error. So in the mean square error, what we essentially do is that we calculate the difference at each point, and we just square the difference. So for example, let's say we are at this point and the value function is 5 and the approximate value function is 3. So the mean square error here will be, or the square error here is at this point 5 minus 3 square, which is equal to 4. And you add this for all the states. Whatever I did for one state, you add it for all the states, which is represented by this summation sign over here. So we are going to tune our weights such that the mean square error is reduced as much as possible. That is our whole objective. And there is a very nice way to visualize this mean square error. As I said here, the approximate value function is matching the true value function. So the mean square error is 0. The mean square error is given by this red shaded area. So here you can see the mean square error is 0. And then as you move away from this intersection point, the error keeps on rising. So if you add all these errors, it is equal to this shaded area, which is shown in red. So our objective is to basically reduce this shaded area as much as possible. It looks kind of big here because we are using a different scale. You can see the scale is on the right. The maximum is 0.08 and the minimum is 0, which occurs at this intersection point. So this visualization can be used to understand, okay, this entire area is what I want to minimize, and that is the whole objective of the value function approximation methods. Okay, so in the above graph, we are going to the main thing is that we have given equal importance to all the states. Now, what happens in a actual reinforcement learning problem is, let's say you have like a lot of states, you have a distribution of states, and the agent only visits certain states more number of times. but other states are not visited. So it makes sense that we give more importance to the errors which arise from the states which are visited more often by the agent compared to states which are not visited at all. And this will make sure that we are giving importance to some states and we are giving less importance to others. Now, this is not included in this mean square error formulation because, as I said, we are summing up the mean square error at all the different states. So, how do we include this? Let's take an example. First, let's understand what is the meaning of some states are visited more and some states are visited less. So, what I have shown here is the state distribution. Uh, so it looks like a tall mountain, and the peak of the mountain is at s equal to 0, which means that this state is visited maximum number of times. And as you move to the right, the states are visited fewer and fewer number of times, and as you move to the left, the states are visited fewer and fewer number of times. So you can have a lot of distributions. Let's say you have a distribution like this. What does this mean? This means that all the states are visited equally. But we are going to assume that we have a state distribution which looks like this green mountain with a single peak. So here what happens is that the state 0 is visited the most number of times and the visits decrease as you move towards the left and towards the right. And this value is captured in terms of probability. So here the value is zero point zero 0.04, which is the maximum value, and it dies down. So this is called as the state distribution, where the states which have more probability of visiting have a higher value, and the states which have low probability of visiting have a lower value. Now, I want all of you to pause at this point and try to think, how can we modify this objective function so that we take this state distribution into account? Remember, we want to give more importance to the states which are visited more number of times, which means the states which have a higher value of the state distribution, which is denoted by mu of s. So, let's say this is our objective function v of s minus v hat of s comma w. What will happen if we simply multiply this by mu of s? What this will do is that if my mu of s has a very high value, let's say mu of s is zero point 0.8 or something, then if this difference is, or let's take an example of by taking s as 0, we'll take this state to be 0, which is the peak of the mountain. So it becomes mu of 0 into v of 0 minus v hat of 0 comma w. So if mu of uh, if let's say this difference is very high, then my entire product is going to be very high because this mu value is the highest, which means that I am penalizing my approximate value function more at points which have a higher value of mu of s. So that is what I will do if I make this multiplication. This multiplication, in order for this entire product to go down, I will penalize my approximate values of the approximate value function at states which are visited more often because they will have a higher value of mu of s. And this is exactly what we want. And that's why, to give more importance to states which are visited more, the objective function is modified as this. Now we want to minimize this error. This is the crucial difference from traditional machine learning algorithms where you might have seen the mean square error, but in reinforcement learning we have to multiply by a quantity called mu of s, which is called as the state distribution. You might hear me say this word multiple times, and it's Really simple, it states that state distribution captures how many states are visited, how much frequently. So this can now be visualized as follows. Previously, we had this shaded area which was in red, right? Which was giving equal importance to all of the different states. Now, if this is the mu of s, if you multiply this by the mean square error, you get a square distribution which looks in as blue. Now, previously, what were my conclusions? If you just focus on the red shaded area, I would think, oh, okay, one has the maximum error, so I need to reduce the error at one, at the state one. And that was wrong because state one was not visited at all. And my new conclusion is that, oh, okay, so I need to reduce the error from minus 0.25 to 0.25, which makes sense because these are the states which are visited most often, as you can see from this from this mu of s graph. So this is what we are trying to do. We want to minimize this, and this objective which we want to minimize is often called as VE, uh, which is the value function, the approximate error in the value function estimation. The notation does not matter. What we need to understand is that the function is given by this, which is a multiplication of the state distribution and the mean square error between the true value function and the predicted value function. Now, this is what we want to minimize. Now, how do we minimize this? That's the question which has puzzled machine learning researchers since a long time, and there is a common answer to this which you see in every single machine learning algorithm, which is called as gradient descent. And this is exactly what we are going to apply to minimize this function. Before we understand how gradient descent is applied to this problem, let's try to build some kind of intuition about the method of gradient descent. So let's say we have a function which looks like this, right? It looks like a pretty complicated function. And let's say this is the function that we want to minimize. This is our objective function. Now, let's say I start at point A, at which the value of the function is high, right? Because the the curve is sloping upwards at that point, so the value is high here. I know that point B is somewhere at the minimum of this, so I ideally want to reach point B. The question is that we now start at point A and we want to reach to point B. How do I reach to point B in the most effective manner? Imagine you are at the top of the cliff and you want to reach at the bottom. There are multiple directions you can go, but to reach in the fastest possible time, you will choose a direction which has the maximum slope so that it takes you down the most. That is exactly what gradient descent does. At every step of the way, you choose a direction which is the gradient because it gives you the steepest slope at any point. And gradient descent says that to go from point A to point B, take small steps in the direction of the gradient. And this is what is the intuition. Let's say you start with this step and you take a small step, you take another small step, and slowly you will reach here. You will reach the minimum. So you start with a random value, and then you calculate the gradient, you update the parameters, and you reach to the minimum. Okay, so now that we have understood the intuition, what we want to do, we want to go from A, we have started at A, we want to go to B, and we want to do that by taking gradients at each step. Okay, so let's think about what is on what are we taking the gradient with respect to. So that is an important consideration which we will understand now. So basically, we want to optimize the weights so that, or we want to control the weights so that this objective function is minimized. So what the descent tells you is how do you change the weight in a way that the error moves in the direction of the steepest slope. So let me explain that with a 2D example. Let's say this is the error. This is the error which we described before, and let's say this is the weight. Let's say we have a vector of a single weight value, and I start from this point. So clearly I want to reach over here, which is the minimum of this. And what gradient descent tells me is that you start with this weight value which is on the left, and you take a small step, you update the weight value, you take another small step, you update the weight value, and slowly you reach to the point where you get your correct weight value, which is W min. Now, this is exactly what we want to do. So we start with a random value of the model parameters, like we did over here, W0. We calculate the gradient and then we update the parameters. Now, how the parameter is updated is given by a simple formula, which is theta equal to theta minus uh, n of grad of the loss function, where n is the learning rate. So this entity, this is the gradient, and this is giving the direction in which I want to move to reduce my loss. So it is essentially the slope. So in this example, the slope at p, this is equal to grad of this function, the slope at point p. So I am moving in the direction of slope, and what is my step size? My step size is given by eta. So this is how I am changing my function. We have a negative sign here because we want to minimize the loss function. If we had to maximize, then we would have taken a positive sign there instead. In our problem, notice that this theta will be replaced by weights, because the weights are the parameters which we want to control. The weights are in our hand. The loss function is the mean square error multiplied by the state distribution, which we looked at before, and we choose eta equal to alpha by 2. It will become clear why we use alpha by 2 over here. Now what we do is that we use this objective function that we want to minimize, and we use this equation. So theta becomes wt plus 1 is equal to wt, which is the previous weight value, minus alpha by 2, which is the value of our step size or the learning rate, grad of this function. Notice that the state distribution here we have neglected for the purpose of simplification of the mathematical calculations. Now, when we take a gradient of square of any function, so for example, if you have x square or f of x, and you take d by dx, then what you get, or let's say f square, and d by dx is 2f of x into df by dx. This comes from the chain rule. So this is exactly what we do over here. When you multiply, this 2 comes at the bottom, and this 2 comes at the bottom. That's why we have alpha by 2. So this 2 and 2 cancels, and then you get uh, v of pi st minus v hat of st comma wt into grad of v hat. Now notice that this negative sign has been converted to positive because this negative is multiplied by this negative. So this is the update rule, where this is the gradient of the approximate value function, and this is the difference between the true value function and the approximate value function. So what we are essentially doing here, you can visualize. Let us say we have two weight parameters now, W1 and W2, and we are starting. Let's say this is our function. We are starting somewhere here, and the minimum of loss happens somewhere here. So after applying gradient descent, this is step number 1, step number 2, step number 3. Slowly, after taking maybe 100 200 steps, We obtain our values of W1, W2 such that the loss is minimized. That is the whole objective of this whole process. We want to tune our weights such that our loss function is minimized. And how do we tune our weights? We move our weights in the direction where the gradient of the loss function is the steepest. That is the intuition behind it. The mathematics only involves this chain rule and the gradient operation. That's all. Now, you might wonder what is this gradient? What am I doing over here? So, let's say you have two weights, W1, W2. Then this gradient is represented by ST, comma WT, comma dou W1, comma ST, comma WT, dou W2. So it's a vector. So whenever you are trying to visualize these equations, always consider small numbers so that it helps you understand what's happening properly. Okay. So now this is clear. Let's go ahead. The question now that we want to address is, which was the first of the two issues which we covered before. Notice that this is the true value. This is the true value function which we are not aware of. So this is the issue of the targets not known, which we mentioned before. If the target is not known, then how can we perform gradient descent? We are not aware of what is the true value of the target at all. So how can we perform gradient descent? Because we cannot substitute the true value in the formula. And this is something which we will understand. I want you to pause over here and think, how can we provide an approximation to the value function? It is something which directly comes from the classical learning methods, classical reinforcement learning methods, which we looked at. Basically, what we want to do is we want to find an approximation of the true values u of t such that the expected value of this approximation matches the true value function. So, whichever approximation whose expected value matches uh, the true value function will do. Now, this might take you back to Monte Carlo. In Monte Carlo, remember what we did was uh, after the agent moved to any state, we calculated g of t, which is the sum of rewards at that state. And if you add up all g of t's and average them, then you will get the true value function for a state. The reason is that this is the exact same formula which I have for the value function of a state also. So value function of a state is the expected value of the sum of returns, which is RT plus gamma, RT plus 1, etc. And these sum of returns are nothing but the G of t, which is the return which we use in Monte Carlo. So one such approximation is the Monte Carlo return. Even if you are not able to recall that formulation right now, it's quite intuitive. If you are at a certain state and you reach till the end of the episode, you add up all the rewards. That is one estimate for the value of that state. But if you keep on doing that 100 times, you will reach closer to the true value of the state. So we are taking just one return. So I agree that it's not same as the true value of the state, but we have to take this return multiple times, and then it will approximate the true value. In other words, the expected value of this return is going to match the true value of the state. So expected value of this return is going to match the true value of the state. Okay, so we are going to replace the true value function by the return from that state, which means that when the agent encounters a state, we are going to add up all the returns towards the end of till the episode is completed, and we are going to use it as a approximation to the true value function. This is how the problem of the value function not being known or the output not being known beforehand is solved. You might have never seen this in supervised machine learning problems because the output is already given. You don't use an approximation to the output. This is what makes reinforcement learning problems so unique, that you are using an approximation over here. Now, there is one small subtlety here which all of us should understand, and that subtlety will will first take us to this problem. Now, here we are replacing this by g of t. Now, remember that when we were calculating this gradient, so we are calculating this gradient of g of t minus v hat of s comma w whole square, which is equal to 2 times this into gradient of g of t minus v hat of s comma w minus gradient of this. This is the simple chain rule which we saw here as well. Now, what works for us is that this gradient is equal to 0. So, whatever formula we used for the chain rule, exactly it is valid for Monte Carlo return as well. So, we need not worry. You can do this calculation again by looking at this. It's simple and straightforward. Now, okay, so we have used the Monte Carlo return for this approximation. What if we use the temporal difference target instead of the Monte Carlo return? Well, the temporal difference target is quite interesting because what it says is, it says that okay, my value function of a state is the expected value of all of these returns. Now, the temporal difference return says that I'm going to approximate this by rt plus 1 plus gamma times whatever comes later can be written as value function of st plus 1. And this is an approximation whose expected value can be approximated to be equal to the value function of the state, which is exactly what we used in the temporal difference methods. So we can wonder, okay, to calculate the Monte Carlo return, we have to wait till the end of the episode. Why don't we use a target which is just this, so that the gradient descent rule simply becomes like this, where instead of the true value function, we have replaced it by the temporal difference target. If the TD target or temporal difference target is not coming to you right now, naturally it's fine. You can either go back to the temporal difference method or understand that this is quite intuitive because we are replacing the act of adding all rewards by adding just the immediate reward and taking the discounted value of the next state. You will see this pattern multiple times in even dynamic programming as well as temporal difference methods. Now, there is one problem with this though. Uh, and some of you might have identified that the problem is that this value function is dependent on the weights. So here also we should have a hat, v hat. So since this value function, which is the value function for the next state, is dependent on the weights, remember in the chain rule, we had assumed this derivative to be zero because the Monte Carlo return did not depend on the value functions. But if we have a value function, then we have to consider the derivative of that value function as well, and which will mean that this formulation will not hold because we will have one more derivative. So the actual formulation will also have this. So this term will be replaced by grad of v hat st plus 1 comma wt, this term will be replaced by this term minus grad of v hat st plus 1 comma wt. I encourage all of you to use the chain rule again and see whether this is true or not. But this is it. It turns out that you cannot use the exact same formula. But what people do is that they choose to ignore this anyways. They say that let me ignore this and I'll just consider the gradient of the approximate value function for this state. So that's why this is called as the semi gradient method. And theoretically it's not completely accurate because you have to include one more gradient here, but that gradient is completely neglected. That's why it's called a semi gradient method. Now for the above methods to work, uh, what we saw above was we saw that okay, we have to find an approximate value function which matches the true value function. So firstly we calculated what is our loss function that we want to minimize, and then secondly we saw let's use gradient descent method to minimize this loss and update our weight parameters accordingly. Then we saw, okay, but we do not know the true value function. So what do we do with our target? So we replace our target with the Monte Carlo return, and we can also replace our target with the temporal difference return. In this case, we are making an approximation by neglecting the gradient of the approximate value of the next state. So we call this a semi-gradient method. Okay, so now great, we have the update rule ready now. Now we have the update rule ready, we know how to modify our weights. The only thing pending is that how do we write this value function in a functional form? Now this is something which is pending and we have to think about it. Uh, so I have not discussed that yet. I have just told you that the value function can be written as some function of the weights. But what is this function of the weights which the value function can be written as? So it turns out that there are multiple methods of explaining this, and we are going to briefly cover these methods in the next lecture so that there will not be a lot of information presented to you in this lecture. In this lecture, I just want you to be familiar with the function approximation method. How do we approximate the value function? How do we solve the issue that we do not know our target but still we want to find an update rule? So we are doing a significant shift now from the classical reinforcement methods, which use the trio of dynamic programming, Monte Carlo, and temporal difference learning, to function approximation, which forms the basis of modern reinforcement learning. Thank you very much, and I'll see you in the next lecture.